We all listen to music nowadays. It has become a cultural norm. But have you ever stopped to think about how music actually works? A normal song has an instrument that makes different sounds and a person singing. But why do those instruments make those exact sounds? And what makes the sounds different from each other? And how does this even function in digital music using digital applications? Well, let's look into that. Now we have opened the beautiful application of Microsoft Paint, and we need some fundamentals to know what really is sound and why does a music release sound. Now, the very most fundamental thing about sound is that sound is something considered a wave. Now we all know waves, from for example a beach wave. We've heard that word before, but waves are something. The sound waves are something more complex. Now we have here Microsoft Paint, and let me explain to y'all how what is a sound wave really. Now a sound wave is something which moves in this type of direction. If we have a graph like here, this is like, let's say, wait, no, let's say that this is our graph. Then a sound wave would look something like this. It would start from here, the origin, and then it would go like this. And this is what we call a sine wave, right? A sine wave is, as from its name, it is a graph of sine x. And why does this represent the sine wave? Because, well, of course, it doesn't represent all sound, but this is just a general representation of sound. This is what a wave looks like. Even in real life, if we see a wave in real life, a wave really just doesn't move like this. It just moves like this. Like if you have a rope and you start like moving it up and down using the rope is really going to move like this. This is the movement of a rope. And the rope is considered also a wave, and sound is the same thing. Now, what really is a wave, and why does it even look like this? Like this type of M look. But it's actually not. It's supposed to be more smooth. Anyways, why? Well, this sound wave is considered something even deeper called a longitudinal wave. Now, we're getting to some physics territory here, but to make it simply, well, a wave is the movement of particles, right? It's an energy transfer, but the particle is not actually moving like up and down. No, in a longitudinal wave, a particle is moving like this. It's moving to the right. One particle bumps the other particle, and that bumps another one, and that bumps another one, and it's an infinite cycle. So it's like it kind of looks like this, and then spaces between them. Wait, no, let me draw it more accurately. It's like this, and then spaced, and then sometimes we have areas of deep, and this is where the energy is going, and spaces, and like this is like the coils that you get always as a present in like any festivity that moves up and down. Yeah, if you move it like this, it's like this particle moves this, and then this moves this, and then this moves this, and if you graph it, it is going to still look like this in the end. It's a very beautiful thing. And now let's draw this sine wave again. Now let's look at stuff here. Now the x-axis is t, the time, and this is the amplitude. Now I'll explain everything here. Of course, you all know time, and amplitude is simply just the highest point on the graph here. Now remember, this is all a sound wave. Never put that out of your brain. Like, we're still talking about sound here. This is gonna get more interesting. Now this highest point is the amplitude, as I said. And now something is that, let's say that we have a high pitch. Now pitch is like, we all know what a pitch is. Pitch is like the softness, or not loudness, but like the softness or roughness of the voice. Like if the voice is very light on a piano, for example, if you click the rightmost button, it's gonna get a very light noise. But if you click the leftmost one, it's gonna become a very rough noise. Now this is all controlled by this graph. If we have, and this is how digital applications use it. How do they represent the sound? They use sine waves to represent sound, because in the end of the day, sound really is just a sine wave. That's at least how we represent it. This is how we represent kind of reality almost. Now this amplitude, now this is just something that it just is this way. This amplitude represents the volume of the sound. Like if you have a sound going out, then the amplitude is what's called the sound. And if this increases, this is almost like the volume bar. Like if you have here a volume bar, and like this is like 20% volume, and this is like 50. This is basically the same thing. If I draw here another sine graph, let's do a huge one. And now the amplitude is of course way huge, way bigger. This would directly mean that the volume is way bigger as well. This is now volume, not the pitch. So yeah, this is a presentation of sound in real life. And something else is that we have something called a frequency. And frequency is like how it's coming from the word, actually, like we use the word frequently a lot, right? Frequently is just something, is like a derivation of the word of frequency. Frequency is how often we see a wave, like if we, like every second, how much we see of a wave. Like here, this is our basic graph, right? If we draw something, if we draw the same graph, let me draw something better. If we draw the same graph here and we do something like this. Now this is way more like waves. This is like a singular wave, right? This going up thing is a singular wave. Now we have more waves in like one part. We had 2 here, now we have 3. This is the frequency. More actions happening per time. And this actually is the pitch. If we increase this frequency, we also increase the pitch. The pitch gets higher. And of course, if we make it longer, for example, and we make it like this is just one wave, then of course the pitch is going to decrease. And that's really just the sound in music. This is literally how sound exactly works in music. Now let's actually move to an application of this directly in music. Okay, now let's move on to an actual application on this website called Chrome Music Lab. It's a very nice website. Now we have this piano over here. We can click any button, it's like a real piano but digital. And this is the highest pitch and this is the lowest pitch, or it could be vice versa, but it doesn't really matter, it still applies. This is the highest and this is the lowest. Now lowest pitch, I mean, as we just said here, lowest pitch is this one, because pitch is the frequency, and this would be how it would be represented in like an application or visually, because there are a lot of many visual applications of music. So if you would visually apply this graph, it would be applied like this. This graph would be the best visualization of it. Now if we would take something like this would be best applied with this graph, because this has the highest frequency, because it's the highest pitch, and highest pitch is frequency. So yeah, this would be the best representation of it. And if you have something like this, something in the middle here, then this would be the best application, something in between, frequency that's not too high or too low. So yeah, it's very interesting, and this of course applies to every single instrument. You have something here. This is the highest pitch, this is the lowest pitch. Same thing here, drums. Or strings. Yeah, it's the same thing, it's all instruments. It's something so beautiful, how all instruments are simply modeled by something like this. It might seem like it's something so complex and so specific, but when you just think about how this is a representation of every single instrument ever made, it's honestly very beautiful, in my opinion. Okay, we've just seen an application with the piano with one note. We have only been clicking one note, but now in real life, of course, music, like if you have a song that uses the piano, for example, the guy's not gonna just be clicking one note at a time. No, he's clicking many notes. So how is this represented? Now I can't represent it using this application here because I'm on the computer, and on the computer I can't really click multiple stuff at once. But in real life, of course, they can very easily. And this can be represented with something like this. This is a graph on Desmos, but I have it in Microsoft Paint so I can show you more clearly some stuff here. Now, when you have two nodes, well, it's kind of the same thing, honestly. Here, let's draw something here. Let me just bring my own laptop. Here, I have two waves, for example. One that's like this, for example, and one that's like it's double, for example, which is like something like this. Something bigger, for example, doesn't really mean anything. Now, when two waves intersect in physics, physics said that they're both just going to like conjoin really, and they're both going to get added to each other. And so if this had an amplitude of, let's say, for example, 500, and this had an amplitude of 1000, then a new wave would be created, and this wave would be of amplitude 1500. And it would look all weird because they don't necessarily have to interact. Like if they both interact at the same point, like if we see when both waves are on each other like this, then it's going to look like this. But of course, sometimes like it can be interacting like this, and so it's going to look all weird. It's not just going to look like a normal wave anymore. It's going to look more jagged, which is something more like this. It's going to look all weird. It's going to be like something like if you have something like this, it's going to look like this. It's a weird looking wave. And yeah, of course, as well, this application. Oh wait, I went too far back. Wait, whatever. Let's zoom in actually. Man, whatever. I have the picture here. Sorry for the inconvenience. Anyways, we have many waves, and we have many musics, and we have many instruments. And so, wait, why the hell is this 100%? Oh, okay, here. So yeah, we have many waves and we have many instruments that are all playing at the same time. And so, this is why we have all these waves. This could be like an instrument. This could be an instrument. Wait, no, okay, wait, my fingers. This could be an instrument, and this could be an instrument. This one, and then this one. And this could be an instrument, like this could be an instrument playing in the background. That's why it has a low amplitude, so it's like something in the background to soothe. And something like this could be the main instrument, something that's very loud. Now all these have the same frequency, which is something a bit unrealistic, but still, it's for showing purposes. Anyways, let's actually go to this graph, because I actually do have it here. A digital music application could manipulate these waves in a way. Now we don't need to understand any of this like equation and why it's like this, why this is exponent, why this is not. We just want to see how we can manipulate this equation. We can literally change around any of the numbers here, and we can see what changes. Now, of course, what I'm saying here is very simplified because it's a more introductory video. But everything that changes here is for a reason. This changes something, and this changes something. Everything changes something, but let's look at the main stuff that we've taken so far. If we change the two numbers on the exponent, if we change the first one, for example, this would change the amplitude. If I made it lower, then all of these would decrease. You can see the amplitude here is decreasing. And this would, of course, as we said, would mean that the volume is decreasing. If I make it, for example, here 0.7, we can see that what used to be here, like if here, let's take 0.2, what used to be here, if we change it now, see, it went all the way up here, which means that the volume is increasing. And if we look at the other one, sine 5x, let's make it sine 1x. We can see that now there's a lot of more emptiness because the waves are more spaced out because the frequency has decreased. If we increase it here, put it back to normal, this is our normal wave. 10x, we have so much stuff on screen, it's kind of mind-boggling. And we add another 0, it's literally gonna look just like a solid block. Yes, it's literally gonna look solid because there's so many stuff going on here. Because the frequency has just been increased so much. And I mean, if we add so much stuff here, we can still zoom in a lot. It's gonna lag my computer, but we can still see how this is all just waves. But yeah, it's gonna look solid though because it is. Desmos just can't compute all everything. But yeah, this is how sound waves work. Okay, now before I go, I just wanted to give a special shout out to this guy, Ali the Dazzling. very nice video that I watched to understand this, and I was very shocked that a lot of this stuff is genuinely what I just took in physics a couple of weeks ago, because I'm thinking about waves and stuff like that in physics. Very interesting stuff. Yeah, and this guy explained it very well. And another shout out is to my cousin, Nothing Around Us. He has a Spotify account called Nothing Around Us, and yeah, I had a long talk with him about music, and he explained a lot of stuff to me, and about how music works, and how it works related to physics and math and all that stuff. So yeah, thank you to my cousin, and go listen to his music. Give him a follow. Listen to his music. It's some very high quality stuff, and he's very passionate about his stuff. And I was very shocked about his knowledge, because I take like some very high level physics. I take physics HL and IB, and somehow he knew everything that I took, which is very impressive. So yeah, very impressive stuff. Give this guy also a like on his video. His video was very cool, and also my cousin, of course. Yeah, go listen to his music. Give him some love, and yeah, thank you guys for watching the video, and hopefully see you in my next video.